Welcome to the Deep Dive. Today, we're getting into an absolutely foundational source. It's a wide-ranging conversation with two of the most influential people in modern AI. We're talking about Jeff Dean, Google's chief scientist, the mind behind systems like MapReduce, and Noam Shazeer, who co-invented the transformer.
Yeah, and our mission here is really to distill what they shared. This is, 5 decades of combined experience. It covers everything from hardware to huge systems to algorithms.
Right. It's not just how do we get LLMs.
No, not at all. It's about the foresight they had, the big technological shifts they had to navigate to unlock all this potential. The whole story is really about transformation through, extreme scale and optimization.
Okay, so let's start there. Let's start with their history. They've both been at Google for nearly 25 years, since it was tiny. And they talked about those early days when Jeff Dean, who'd basically written everything, he literally knew everything.
Which made him the default mentor for everyone new. A bit intimidating, I imagine. He talks about this progression of growth. First, there are maybe 25, 26 people.
And you know everyone's name.
You know everyone. Then you hit the next phase, where you stop knowing all the names, but you still know every single software project that's going on. You can still track the innovation.
Until you can't.
And that's the final stage. He gave this great example of getting an email announcing something called Project Platypus.
And he had no idea what it was.
None at all. Hadn't even heard of it. And that surprise, that feeling of realizing the innovation had scaled beyond what any one person could possibly track, that really captures the whole journey.
That scale is just staggering. And what's so interesting about Noam's story is that when he joined in 2000, his motivation wasn't, to build the future of search.
Not at all. It was totally pragmatic. He said he applied just because it was his favorite search engine. The plan was to work just long enough to save up some money.
Right, to build a little nest egg so he could leave.
Exactly. So he could leave and then pursue what he really wanted to do, which was full-time independent AI research.
And the incredible irony is that Google ended up being this terrific place to work on AI.
The perfect place, really.
Because the company's core mission organizing the world's information, you can't do that without AI. It's an AI problem at its heart. So his financial runway just became this infinite algorithmic runway.
And that foresight goes back even further. If you really want to see the roots, you have to look at Jeff Dean's undergraduate thesis from 1990.
1990. I mean, you have to remember, neural networks were basically in the academic wilderness back then.
Oh, completely. But there he was, experimenting with how to parallelize backpropagation on a 32-processor hypercube. He was testing 2 different methods.
Okay, so what were they?
Well, one was what we now call data parallelism. You give different training examples to different processors at the same time. The other was model parallelism, where you actually split the neural net itself across the processor.
Oh, what was a big takeaway from that?
The insight was just profound. He realized that the basic idea, the neural net abstraction, was right. But his conclusion was that they'd need, and this is a direct quote, about 1 million times more compute for it to work on real problems.
1 million times. So he saw the path, but also saw it was decades away.
Exactly. A 7 order of magnitude prediction. That patience is just incredible.
And you see that same focus on scale and optimization almost 2 decades later. So fast forward to 2007, they're training this huge 2 trillion token n-gram model for machine translation.
Yeah, Chinese and Arabic into English. But they hit a major wall. A physical bottleneck. Just to translate one sentence, the system had to do 100,000 random disk seeks.
100,000. So the translation took...
to 12 hours.
12 hours for one sentence.
Yeah. And this is where that classic Jeff Dean optimization comes in. The solution wasn't just, buy faster disks. It was algorithmic. He designed a new way to represent the data, an in-memory, super compressed version, and spread it across 200 machines.
And the result?
Translation time went from half a day down to 100 milliseconds. But what's really key here is that even though they called it a translation system, it was the start of modern language models. It proved that if you have roughly infinite training data, you can learn these incredible latent representations of language.
So they had the algorithmic proof, but that success kind of hid this bigger problem that was brewing for the whole industry, right?
Yeah.
General CPUs weren't getting faster at the same rate anymore.
Moore's law was slowing down. That jump from one fabrication process to the next, it went from, 18 months to every 3 years?
So they had to pivot.
They had to. They couldn't wait for general CPUs to catch up. They needed specialized hardware. And that meant TPUs and ML-focused GPUs. The core idea here is really simple. Arithmetic is cheap. Moving data is expensive.
This is that n cubed versus n squared thing.
Exactly. Matrix multiplications are at the heart of deep learning. The math, the number of operations, scales as n cubed, but the data you have to move only scales as n squared.
So the chip is often just sitting there, starved, waiting for data.
Right, it's memory bound. So the opportunity cost became obvious. Why waste all that chip space on general purpose stuff when you could just fill it with tons and tons of simple arithmetic units? And that's what a TPU is, fundamentally. It's a reduced precision linear algebra machine.
Which leads to this big co-design trade-off. To get the efficiency you need for global scale, the hardware teams are always pushing for lower and lower precision, INT4, FP4.
Even one-bit quantization. And you can imagine the algorithm designers, they hate this. Losing precision feels risky. It can introduce errors.
So I imagine those meetings get pretty tense.
Oh, for sure. But the hardware team has the ultimate leverage. They basically say, look, if you don't tolerate this, we won't build the specialized chips you need. The trade-off is something like you accept a little irritation, and in return, you get 3 times the throughput.
And that willingness to push the limits is what's driving everything today.
It is. Which brings us to the next big problem. Inference. And specifically, context size. They point out that models today can hallucinate because their knowledge is, well, it's squishy. It's all compressed into these billions of parameters.
But the knowledge in the context window, the stuff you just gave the model, that's sharp, it's clear, thanks to the attention mechanism.
Right. And the ambition now is to let models attend to trillions of tokens. Think about that. The entire internet, all of your emails and documents, all at once.
That sounds computationally impossible.
With the current architecture, it is. Naive attention is quadratic. Double the context. You quadruple the compute. It just doesn't scale. You need new algorithms, new approximations to make it work.
But they see this incredible room to grow because the cost difference right now. They made this comparison that talking to an LLM is 100 times cheaper than reading a paperback book.
And 10,000 times cheaper than talking to a human customer support agent.
So we're basically underspending on AI answers.
Massively. And what that gap means is we can afford to apply much more compute at inference time to make the model think harder. It's not just a simple query response anymore. It's about iterative exploration, searching for better answers, giving you a dial to say, okay, spend more time, get me a more reliable answer.
They gave a really cool algorithmic example for this, the drafter-verifier model.
Yeah, that's to get around the single token at a time bottleneck. Instead of using the huge model to generate one token, you use a tiny, fast drafter model to predict, say, 4 tokens ahead.
So it speculates.
It speculates. Then the big, powerful model just comes in and acts as a verifier. It checks all 4 predictions in parallel. It's way, way faster.
This kind of optimization is what sets up their next big prediction, this hyper-acceleration feedback loop. It's not just about chips anymore. It's about the AI improving its own development.
Exactly. They argue that algorithmic improvements are now driving progress just as much as hardware, maybe even more, and that creates these feedback loops.
So for research,
you can have automated systems generating and testing thousands of new ideas. Instead of a human researcher trying 1 or 2 things a week, an AI could explore 100,000 ideas at small scale. That just changes the game.
And the same idea for designing the hardware itself. If AI tools can cut chip design time from, say, 18 months down to 9,
then the physical manufacturing time, which is maybe 3 to 5 months, becomes your main bottleneck. When you speed up both algorithms and hardware design at the same time, well, that's when you get a potential explosion of capabilities.
And they're talking about a world GDP increase of 2 orders of magnitude, 100 times bigger, assuming we solve the energy problem, of course.
Which is a huge assumption, but it leads directly into the safety question, AGI alignment. They frame it as an engineering problem, a very, very hard one, but still an engineering problem.
Like developing software for an airplane.
Exactly. But with this unique complication of a rapid, self-improving feedback loop. So their safeguards are all about control. Human oversight is non-negotiable, using AI to analyze its own output because analysis is easier than generation, and controlling everything through APIs and strict responsible AI frameworks.
That focus on systems and architecture leads to their final big idea, moving away from these single monolithic models.
Right, moving toward sparse, organic structures that can do continual learning. This all builds on the mixture of experts idea.
Which just means you only activate a small, relevant part of the model for any given query.
If you ask a math question, only the math experts fire up. The key is efficiency. The future vision, which is built on this infrastructure called pathways, is to let the model grow organically.
Instead of the rigid structures we have now.
Exactly. The ultimate goal is to have independent modules. A team somewhere could train an expert on a niche language or on Haskell code and then just hook it into the main system without retraining the whole thing from scratch.
That's a massive shift. It allows for parallel development. And it must change the deployment model
But
completely.
totally, you could have varied costs. That expert on Tahitian dance that's rarely used, you can page it out to slower memory. You can also have personalized modules trained only on your private data, keeping it totally separate.
But to make that work, you need this huge single-instance infrastructure, like one of Google's TPU pods, keeping all those experts ready to go. It's a whole new data center paradigm.
So to bring this all together, the story of modern AI, through their eyes, has always been about solving problems of extreme scale. From seeing the need for 1,000,000 times more compute back in 1990, to making translation work in 2007, to co-designing hardware now, it's all about optimization.
And their final piece of advice was about humility. Being ready to drop your most cherished idea the second a better one comes along.
Yeah, that flexibility is key.
And that leads to a final thought for you. If they're right, if we're really about to automate research and development itself, and if AI compute is already 100 times cheaper than reading a book,
Right.
what happens when you have millions of AI agents designing, coding, and debugging the next generation of AI? This isn't just about speeding things up. It could fundamentally change the timeline for major breakthroughs.
And if that vision of a continually learning organic AI model actually comes true, a system where you can just surgically add new expertise on the fly, how does human knowledge even work anymore when the AI itself becomes this constantly evolving thing, not a fixed program that we write and debug?